Hi, so I'm Tux. I work at Nucypher. I'm a cryptography engineer there. What we're going to be going over today is fully homomorphic encryption and how we get here from other secure computing solutions. So, as a brief overview, I have a lot of material to cover, by the way. So we're going to go through this really quickly, and if we have time for Q&A afterwards, I would love to talk about it and get some feedback from you guys on what you understood and what you didn't, so I can clarify it. So we're going to be going over what secure computation is, what technologies can be used for secure computation, multi-party computation, trust execution environments, fully homomorphic encryption, the shortcomings of each approach, and solutions for an FHE-based approach, and what Nucypher has contributed to the space for that. In the previous talks, you've probably heard people talk about MPC and Ts as well. And so if you're going to be we're going to be discussing really the specifics of those solutions and why they may or may not be good for the applications being developed today. So what is secure computation? This is a diagram of a two-party computation protocol where Alice knows some data point or variable X and Bob knows some variable Y. And they want to perform this function F. If you see right at the very top where the arrows are, they want to perform some function F with those two inputs X and Y without revealing any of the information on that. So what does this mean for secure computing in general? Parties involved have a requirement for privacy to some degree. Usually they have a need to perform some computation on data that is considered secret or private. Requirements for zero knowledge are not required, but can be present, meaning like we don't want to reveal some information in that computation, so some of the information on those variables. Sometimes that requirement is there, sometimes it's not. But in general, in secure computation, there is a lack of trust in the computational setting. What this means is we're talking about adversaries and threat modeling. You're probably familiar with network level adversaries. You know, if you're in China or Turkey, you may have a government that is sophisticated that does deep packet inspection and where things like encryption may not be as great because it starts flagging your traffic. What that means is we just have some adversary that is seeking to break the confidentiality or gain some knowledge about that computation you're performing. Solutions can exist in both in hardware and software. And while we're going to go over the specific solutions and what that actually means, but really what it just means is that something can be written in hardware for secure computation, or something can be made in software, so something like a multi-party computation protocol or an encryption scheme or something like that. The threat models vary greatly between different solutions. So, for example, the threat model you use for something like fully homomorphic encryption may be vastly different from the threat model defined by Intel's SGX. And what a threat model is, it pretty much says, here's the attacks that are able to be performed on our technology, and here's what we're trying to prevent against. Some threat models pretty much exclude things. They say, we don't care about that type of attack. A very common one is, we don't care about somebody who has local access to a machine, because typically once you can touch a keyboard of a computer that's running or have access to it, you can violate it in many ways to gain access to it. So in those cases, the threat models are very use case specific. So it depends greatly on what that implementation is. So let's dive right into multi-party computation. Multi-party computation is a software-based security protocol. Security reduces to the cryptographic primitives used, like Shamir's secret sharing. And in many cases, it's built upon principles of mathematics, usually. So when we're saying software-based, like I said, it just means that we can implement something using mathematical security or provable security that says, if somebody can break this, then they can usually break some mathematical hard problem. Obviously, there are multiple parties involved, and data is shared between all the parties. The computing parties gain no knowledge of the inputs to the circuit, and where that circuit is a actual computation. And when you hear the word circuit, I want you to think of like program or logic flow. The input data is split and shared at the beginning of the protocol and reconstructed at the end. So if you can see in the diagram here, at the very beginning, a party will say Alice splits up a secret piece of data, usually like some plain text. She splits it up and distributes it to multiple parties. Those parties then perform our second stage here, that computation. That's the circuit being performed that's represented by that binary addition, that binary multiplication there. And then at the end, that reconstruction is usually Alice or the person requesting that computation to be done, retrieves all the inputs back out from that computation of the output of that circuit from each party and performs a reconstruction, usually associated with that secret sharing scheme. So at that point there, that data is then put back together, and they've achieved the output of that computation without usually the people in the middle performing the computation actually learning anything about those inputs. So now we're going to get into trusted execution environments and what they are. So as you can see in our diagram here, I'll go over that just in a second, but it's a hardware-based security protocol. So what that means is security reduces to the safe implementation of an enclave on a processor. That's specific towards this solution here. We have a platform in that diagram, usually something like a CPU or a trusted platform, TPM, that's usually a chip on a motherboard. What I want you to think of when you hear hardware-based security is a separate partition in silicon. What that means is we have like a little piece on the actual silicon of a chip, of a processor, of a motherboard that acts entirely different from the rest of the computer. And there is an API in which you access it, but there's only some functions you can do. And it performs those away from the rest of the machine, where the rest of the machine should not typically have access to it. Most implementations are vendor specific, in our case, proprietary and closed source. So if you're building open source technology, this becomes a major problem. Things like Intel SGX, which has become very popular in the blockchain space, AMD PSP, ARM Trust Zone. These are examples of trusted execution environments that are accessible to the consumer class. So it requires a client API. You see that little brown box. It could be brown. I'm colorblind, so I don't know what that is. But it says T client API. And when you build an application in the rich execution environment there, meaning if you're executing some Python code or some C code or Rust, for example, you're going to typically be executing stuff in the on the kernel, on the operating system, where other programs have access to it. That's the rich execution environment. And what you're going to do is when you access other T's, you're typically going to be accessing that T client API, and it's going to access the core API inside that other chip. And that's what we call the trusted execution environment there, where your code doesn't have direct access to that data being executed there. These things can be function specific, and you're typically going to see these more often than not. If you know a UBHSM, that can be considered a trusted execution environment. It's a hardware security module that performs signing, key generation, encryption, things like that. But things like Intel SGX are more generic, which let you do a few other things beyond that. But typically these solutions here are increasingly problematic because of hardware and because of hardware security, and I'll get into that a bit later. But typically the function-specific ones like the UBHSM are typically better for security than the ones like Intel SGX, which are more generic. So now I'm getting into the big thing that everybody came here for, fully homomorphic encryption. It's a software-based security protocol. It's a form of encryption. It's implemented with lattice-based cryptography and reduces two mathematical hard problems associated in that space, specifically things like learning with errors. I'm not going to dive into the technicals of what that exactly is, but when you think learning with errors, think about like elliptic curve cryptography with discrete logarithms and things like that. A major benefit to this is that it's quantum resistant. So if you're worried about quantum computing, which you don't really need to be right now, but to be fair, it is quantum resistant. Solutions exist for both single and multiple parties. I'll get into that a bit more later. The function is computed directly on the ciphertext. So what that means is we take an output of an encryption function, and we can actually perform a program or some logic, digital logic, on that ciphertext directly without ever knowing what the underlying plaintext is. So the output of the homomorphic computation is equivalent to the computation performed on the plaintext. So if you were to add or multiply two ciphertexts together, it would be the exact same equivalent as adding or multiplying two plaintexts. That should help. This diagram here makes it a bit easier to understand that, where you can perform the same function f on that plaintext m and get the same exact function that you had performed on the encryption. Typically, there's two keys used. This is for security, and I'll go into that also a bit later. But we have an encryption key used to encrypt and decrypt the data, and a computation key, which a party needs to actually perform the computation on that data. So diving into some pros and cons on multi-party computation. Circuit design in MPC is pretty nice. You can construct it with Boolean logic gates. Debugging is straightforward. You can perform a reconstruction operation in the middle of a circuit, meaning that you can just say, oh, give me the data now so I can figure out what my logic is doing. You can reconstruct it. Security is awesome. It reduces to relatively simple secret sharing schemes. That's great. However, circuit design, some cons about that. It requires additional zero-knowledge proofs to make the protocol secure, which can add a ton of complexity. And it also also branching is either impossible or kind of complex. Operations are performed on split plain text data. So still plain text data. Collusion results in the breaking of the confidentiality of that data. Complexity grows linearly with the circuit size. I'm not going to get into the technicals of this, but essentially what it means is when you start having to include network overhead, when you have to start including zero-knowledge proofs, it becomes incredibly interactive and difficult to scale. There's a large liveness requirement. Every single party needs to be online to perform the computation. An offline node can result in the blocking of the entire protocol from advancing. And like I said, network latency wreaks havoc on these protocols. So if that's a problem in your networking environment, it's probably not going to be ideal for MPC. So now we're going to get into trusted execution environments. And to be honest, I don't really have a lot of good things to say about it, so I'm not really going to talk about the pros for just time. But I will make a solid argument about why you shouldn't use Ts. Debugging is complex. That's not the big issue for me. But there really is no way to peek into the actual processor and say, tell me what you have. It just performs its functions when you say so. So it becomes a little difficult to debug them. Reductions reduce to the difficulty to exploit the hardware, which if you've been paying attention to the hardware security scene, specifically Intel and AMD for that matter, this is a really bad way to base your entire decentralized network and protocol and things on top of, because it's not that difficult to exploit hardware, especially since the threat model is preventing limited local access, which these things don't really do a good job of doing. Look at side channel vulnerabilities like Spectre and Meltdown, which led to Foreshadow, which broke the Intel SGX security, which leaked what we call the attestation keys. Attestation keys essentially said, I can prove that I performed a computation in SGX. And they were able to say, I can do anything and say it came from Intel SGX. They actually made a Twitter bot that you could tweet at it and it would sign anything and say, I was performed in Intel SGX. So Intel SGX, when you hear that, I want you to say, this is not ideal for a trustless environment. So it's called a trusted execution environment. Remember that. It's not great for trustless technology. It requires trust in the vendor. There are no working open source implementations. There probably won't be. There's too many. Like I said, the attack surface on hardware is massive. So this becomes really difficult to do. And updates require hardware replacement. So in the case of Foreshadow, all the Intel processors out there at the time, we pretty much don't know if it was exploited or not. So if you're building on top of Intel SGX, sorry, it's kind of broken. So fully homomorphic encryption, lots of things to say. Can also be constructed with Boolean logic gates. Debugging is straightforward, just decrypt the state as required. There's also schemes to construct it for integer operations if you don't want to use logic gates. Operations, like I said, are performed directly on the ciphertext, and it requires the computation key to perform those operations. They can be performed with single parties or multiple parties in case of multi-key FHE, and it only requires the liveness of the computing party. So in the case of one person, you encrypt data for that person, and then they start performing operations on that ciphertext and give it back to you. So if that person's not available, you can trust anybody who's just going to, just perform the computation. However, branching is impossible when you design circuits, or incredibly complex, and it requires specific algorithms to be constructed. A lot of people are working on this space, so if you pay attention to a few universities that are specific in FHE, we're seeing a much more healthy ecosystem for this, but it's still a problem. Another thing is, fully homomorphic encryption is inherently malleable, meaning that anybody can manipulate the ciphertext. This is a given because we are operating on that ciphertext. If you can perform some logical operation on that ciphertext, clearly anybody can do whatever they want to it. So the best security we can achieve is chosen plain text attack security, or CPA security. Ideally, you want to see CCA security, but that's just not possible with FHE yet, but there's other things we can do, and I'll get into those. Another thing is that bootstrapping, which is the technical term for what we call a homomorphic decryption while inside the homomorphic domain. Kind of complicated, but it enables us to do arbitrary computations on that ciphertext. It requires a strong assumption called circular security. Matt Green has a blog post. I have a link in my presentation with it that will explain it very easily to you. So I recommend you look into that if you're interested. Ciphertexts are large too, by the way. This is the part that everybody's interested in is TFHE, which for a 256-bit security level has about a 16,000 times expansion factor. So if you encrypt 1 bit, it goes up to 16,000 bits. Not great, but this is actually becoming less and less of a problem. We actually have solutions for this, which I'll go over in a bit. Computation keys can also be large. So 100 megabytes for a little key that you distribute to somebody to actually perform the computation. And performance speeds are heavily dependent on the computation environment. So in some cases, we need to have, it will specifically in Nucypher's contribution, we can actually perform these homomorphic computations on GPUs. So of course, it depends on the speed of your GPU to actually perform a fast computation. So getting into this, circuit design for branching would require pre-computed values or interactivity between parties. So if you see that little selection there, that's a branch, in case you've never seen one before. That's impossible in FHE unless you do a few things, because that little if true, if false would actually violate the security, so it's actually not possible. However, compilers are being researched to easily construct these digital circuits. One of our hackathon winners at ETH Denver implemented a WASM interpreter for FHE where they could write stuff in Rust, compile it to WASM, and then we could actually execute that. Chris Pikert, a researcher in the space, has published a compiler for this. It's actually pretty cool. So if you're interested in that research, check it out. There's other schemes too for FHE for different uses. Approximate arithmetic. It's useful for machine learning. So it's like you can, I'm not going to get into that. I don't have time, but TFHE is useful for binary operations. This is what we've implemented with new FHE, and I'll get into that in a bit. But you can do like XOR, NOR, AND, NOT, etc. And then Chimera is an interoperability framework for all of these different libraries, HEAN and TFHE specifically, as well as a few other schemes, which allows you to go between both. So you can do a lot of really interesting stuff there. So security, like I said, FHE is inherently malleable. Anyone with a computation key can perform any operation on the data. However, only the encryption key holder can decrypt it. So you act as a barrier between a lot of attacks there. Like I said, chosen plaintext attack security is the highest achievable security. However, we have leveled FHE, which actually allows us to limit circuit depth and prevent some arbitrary computations, meaning that normally with FHE, we can say, I can perform any arbitrary number of operations, and that's that. However, with leveled FHE, you can say, I can only perform n operations. And with that, we can actually achieve CCA security for some stuff. Zero-knowledge proofs can actually aid in this to prove the correctness of a ciphertext to prevent some of that malleability and increase the security in general just a bit. This is something that Nucypher is actively researching, and we'll be presenting some of our work at DappCon later this year in October. Bootstrapping requires a strong circular security assumption. However, leveled FHE does not require that. Again, see Matt Green's blog post on this if you're interested in learning more about that. So scalability, the thing everybody's interested in right now. Ciphertexts are large, right? 1 megabyte, 16 gigabytes. However, we have ciphertext compression. We can actually use a FHE efficient stream cipher, essentially an encryption function, to encrypt the data symmetrically before computing it in the homomorphic domain. So essentially, you can encrypt the data before you put it into this homomorphic domain itself, and then you can have the computing party decrypt it inside the homomorphic circuit so that it expands in memory only instead of on the disk. This is really great. People have been using this with AES, but there are, if you see this table here, there's actually a few schemes that are really, really nice now that are coming out for that. Newer schemes are coming out, like HEAN, that only have a 40x expansion, which is a huge improvement. And we expect to see many more solutions coming to actually make this far better. So in my opinion, it's not that big of a problem. Performance speeds can be improved through GPUs, ASICs, and FPGAs. We have our library called NewFHE, which has increased performance by 100 times. So we have our speed up here, 100.9 for NewFHE over TFHE. for binary gates, and as well as the much larger speed up for mux gates, which are like ternary gates. I actually believe that NewFHE is the fastest FHE library in the world. So if you're actually wanting to like dig in and figure out stuff and play with fully homomorphic encryption, figure out how it works, it's written in Python. You can easily write homomorphic circuits with it. We used it to win ETH Berlin last year, where we wrote Sputnik, which was the first ever fully homomorphic smart contract. So if you're curious about that, please play with it. We'd love to see what you think. So yeah, that's it. Thank you for coming. Please check out our GitHub at nucypher.dev/newfhe for Nucypher's FHE library, our Discord. Feel free to email me with any questions and I'll respond as soon as I can. Follow us on Twitter. Happy to take questions too, by the way. Thanks. Yes.
I'm sorry, maybe I missed it during the talk. Can you give some kind of definition how you would actually prove that the proxy runs the right computations?
Yeah.
You wrote something about actively researching it.
So when you encrypt something and you're trying to prove that a computation was done correctly, it's very similar to pretty much saying when you perform an operation on plain text. Say you add two numbers together. You can prove that some two numbers were added in zero knowledge, typically. So with FHE, in the literature, FHE actually implies zero knowledge. So the existence of a fully homomorphic encryption implies the existence of zero knowledge proofs, which zero knowledge proofs were found way before FHE was, but that's a side point. But in the case of proving this data, what you're trying to aim to do is prove that the computing party who did a computation actually performed the right one, right? So we're trying to find different ways of doing this, mainly through the use of like different technologies like bulletproofs or even lattice-based zero knowledge proofs. And we're trying to simply say, when we prove that what's called well-formed ciphertext. So when I encrypt some data for you to compute on something, I want it to say, I want you to prove that this ciphertext actually has some format or structure inside of it that I know as the computing party, when I do it, I can still say it still is okay, right? So it's hard to, we can talk afterwards because it's fairly technical and I would actually love to share it with you. Sorry? No, it's hard to explain, but it's typically it can be structure, it can be content. What you're just trying to say is that this ciphertext that I encrypted is actually what I encrypted, if that makes sense. And typically it can be structure or content or something like that. Yep.
To go a little bit further on that, if you were to give someone maybe a ciphertext and then do this FHE, they could kind of just return a random blob that's roughly the size that you as the client would expect, and you're kind of SOL?
To some degree, yes. They have a computation key, so they can pretty much return whatever they want. They can do whatever computations they want. So our goal in research has been able to, what we're trying to aim to do is say, I want to do this circuit. Can you prove to me that you did this circuit correctly?
And is it expensive for the client to check that it was done correctly, if they have the computation key, or are you guys looking to prove it?
That's where our active research is. That's what we're doing. And we'll be talking more about that at DappCon, yeah. Yep. Any other questions? No other questions? Wow, you guys understand FHE really well. All right, great. All right, thanks again, guys.